Hey y'all, and welcome back to Coding with Minh. On today's agenda, my interviewer is going to ask me 2 hard LeetCode questions. No problem. But if you want to make sure you're ready, I recommend Hello Interview. As our sponsor for today's video, they work with coaches who are interviewers at top companies, and it's a great way to practice. So use the code Minh for 20% off your first purchase of FAANG mocks. But anyway, let's get started.
Hi, okay, I'm going to just copy and paste the first problem. Give me 1 second.
Okay.
All right, so given 2 lists of strings, sentence, and words, find the shortest substring such that sentence contains every word in words. And you can see an example there.
Gotcha. Okay, so immediately I have some questions to clarify. Can the lengths of both parameters be 0?
No, they both have to have a length of at least 1.
Of at least 1. What is the upper bound length of both strings, of both parameters?
A long length, but you can assume everything can fit in an integer.
Okay. Are all the words in both parameters lowercase English words?
Yes.
Okay. Is it possible to not find a valid substring?
Sure.
Okay. So in which case, I assume like we're returning an empty string or something like that?
Yeah, that's fine.
Okay. Will our words parameter input ever be longer than sentences?
No.
No. All right. And to make sure, I see the answer is you is not frog. Is the order doesn't matter, right?
That's correct.
Okay. And my last question, there can be duplicates in both parameters as well?
Yep.
Okay, that's tricky. All right, so I have everything I need for now. I opened up drawing mode. I'm gonna tediously redraw the example in sentences. So, okay, you, the frog. Okay. Nope, it's 1. The you is not frog. So sentences, words is just 3 required words that we need in the substring. So you is you, frog. Okay, cool. So just from observation, this one right here, I think, would have 6 words, 1, 2, 3, 4, 5, 6, 3 of which are the required ones, right? So if you is frog, for the is you frog, again, the order doesn't really matter. But immediately, although this is a valid substring right here, it's probably not the shortest one. For one, I can keep reducing the size of this valid substring to exclude the 1. And then we have now a length of 5, which is better than 6, obviously. But we still have and retain the 3 words we need. If I do that again, okay, so we have a substring of length 4. So I think that's the best one I've found so far. Is there a better one? There's a lot of words in this parameter. I think to make my life easier, I'm gonna underline these words in our sentences, just so I can see it a bit better. So you is frog. I think just those 6. So when I look at it like that, that is better. And yep, I think this right here would be the shortest one. That's what we return, but actually not, because I see the answer on line 13. We actually want the actual substring itself, not the length. So we'd return, this as a string, space delimited, it seems like, by the answer. You is not frog. That's a weird sentence, but that's what we'd return. All right, so how do I solve this programmatically? So yeah, kind of thinking of different solutions. The naive one is quite obvious, but we can dispatch a nested for loop where the outer for loop anchors some sort of index. So at the first index here, called I or whatever, but then you have an inner for loop that starts on the same character, same word, and just goes through the rest of the words in our input. And for each iteration, you can check that substring and see if it's valid. Here you have 1 is, for the one is, that's great. You keep going to include one, but one is not in words, so you kind of skip it, keep moving. Same with okay. And so you have you, that's great. You have 2 of the 3 matches. Exclude, you include the, but that doesn't really count for anything. You have frog, and all of a sudden you have, again, a substring of 6. That's great. And the thing is, once you've found a valid subarray and you have the 3 for 3, then you can simply get its length because you have the 2 pointers on both sides of this substring. It'd be just the delta between those 2 pointers, one from the outer loop, one from the inner loop, and see if it's the shortest one. But this does imply that we do need some sort of minimum length, variable to track against. I'd start off with like infinity and obviously be overwritten to something, 6 in this case on this first attempt. But if it is the shortest, eventually the 4 here, we'd update this variable. I think that worked, but it's not just the length again, it's what we return is the actual substring. So we'd need some sort of, result. Perhaps that's the left and right indices, which in this example would be, I think 0. And then if it's 6, then it's 5 indices, index 5 right here to then find the actual substring there. So I think that would work. Obviously, it goes without saying, the time complexity is not super efficient. We have a nested for loop, so that result in an n squared polynomial time complexity. The space complexity would be big O of W, where W is the number of words we're given because of the hash map that we are checking right here, which I can just draw that real quick. So it'd be a hash because I imagine you can look it up really fast in big O1. So that's immediately what I had in mind. Not sure if it's a hash map or hash set, but I'm sure we'll find out. But, I do find, again, it's an issue with this approach. It's not very efficient because, we're having to recompute so many computations, so many calculations. So to kind of show you what I mean, so let's just say from frog here to is, we have all the words we need according to our now target hash set. And the first thing I do is transform words into the hash set, I guess, so far of these words for a quick lookup. But with the brute force, we're having to break out and start all over again where the outer pointer is at okay to then go through the rest of the words. So you have okay, okay one, okay that, and eventually you start at 1, which you do that all over again, you do it all over again until you get to U, where you will eventually get this ultimate answer. You're having to reinspect so many words, because of the nested loop when you kind of don't have to. So my proposal is, this seems like a perfect use case for a sliding window. So for example, if you have something like this, then, you might have the 3 of 3 matches. No, you don't. Maybe something like this, which is great. And you can keep track of that. But once you have the match, you have you, frog, another you, that's interesting, but is, then you can kind of shrink your window from the left and exclude this one right here to now have this window without having to go over something. So in this case, you went down one length, which is great, and you can keep track of that. You keep doing that, exclude the U, but that's okay. That is interesting actually, because and a question I have now is, how do I track currently in this substring what I have? So that sounds like another hash to me, which in, right before, in this case, it seemed like we have 2 U, 1 frog, and 1 is. So then, you can check that against this hash map and, enlarge or shrink your window as appropriate. So you'd have this, you have 2 U's, 1 is, 1 frog. That's okay. You still have 33 matches. You shrink your window to exclude a U, but you still have 1 of each. That's great. You do the same thing. Hey, you found a shorter window. That's great. You shrink it again to exclude the frog, but now you only have 2 entries in here and 3 in here, so you don't have enough matches. that's when you can try to re-expand your window to include not, and then the frog, and then you have enough. You have 3 in here for these 3, and then you can, do all the math to get the minimum length, and if so, then you get the left and right indices to find the actual substring, so forth and so forth. Eventually you get to your answer, right? So I feel like I do like that answer. There's a lot of ideas going on. I feel like I want to do like a informal dry run just to put all these ideas together. So the first thing you do, obviously, this transformation, you have your first window here, which has is. So the first thing I'll do is track that in this, current, I'll call it current hash set. And this can be the target hash set or something of what we're trying to go for. So you have, is, which is great. Next up, you have 1. Technically, I'd include the 1, but, I don't want to, I'm not going to show it because it would take too long. Same with OK. Here you have U as well. So you insert U, and that's an answer, part of answer, because you can just look it up in our target hash and be like, that's a match. Great. So forth and so forth. You have frog here. That's great. You include that. And eventually you get all the way to another use. That's interesting because there can be duplicates as established. Does that matter? I think so. I think not a hash set, but I think we need a hash map because we care, on any given window, we care not just about the word that is in our target, but how many of it we have and how many we need. Because I can imagine our words input here can have, 1 is, 1 frog, but it could have 3 U's. In which case, we have a U, but we need to know that there are 3 as well. And in this case, there are 2, right? The U and U. So I think we definitely need a hash map for sure there. I think what's interesting is, I think because of that, we can't compare if we have enough matches with our hash map sizes anymore. Because just because you have 2 U's, but let's say there are 3 U's here, this example, this, very contrived window doesn't necessarily mean you have a 1-for-1 match just because you have a size of 3 entries here and technically 3 here, because all these keys kind of collapse into 1. You don't have a full match. You need 3 U's, but you only have the 2, the 1 and 2. So I foresee that as a big problem. A hash map is definitely what I'd go for. So let's undo that. Okay, cool. So that, I feel like that makes sense to me. So where was I in this? Just to make sure. I think we were right here to include OK, great. And then you have 1, doesn't matter, all the way until U, right? In which case, okay, we only need 1 of each. And that's great. Oh no, what we do is, we'd be here to get all the matches once you have all the matches. But then from there, you say, well, I want the shortest one. So what I'll do is I'm going to shrink my window to exclude is to get this window, remove it from our hash map, and keep going and expanding our window from the right to include more words in hopes of finding another is. We'd find another U, which is not enough. We expand it once more to get is. We'd reinsert it into our hash map. Fantastic. We have 1 of everything. Well, 2 of U, but that doesn't matter. So you're going to shrink our window, go in the reverse mode and, exclude this. Okay, that's okay. This is a shorter length. Cool. Exclude the OK, exclude the U. That's okay. We still have 3 matches. You take note the minimum length if it's the shortest, and thus 2 indices. You keep going, you keep going. And now you have 2 of 3 matches. So you need to expand it from the right. And you kind of keep going like that. Now you have a match, is this the shortest length? If it is, you say, hey, it's 6, keep track of 2 indices. And then you're going to shrink the window to exclude the OK, and then the, and then eventually you have your ultimate answer. And after that, you shrink it, and then you go to the right once, and you finish with the whole string. So what this means is I'm missing 2 things. I need the current match that I have that's not based off the size of this hash map. And I have the needs as well, which in this example would be the size of, what would be actually the size of that hash map, which is 3. So I need 3 matches, but if they're ever is like, I need 2U's, well, I'd compare it with this 2U's, not just the key, but the count. And then I would increment current to see if it matches needs. Okay, so I think that would work actually, but obviously in the case where there's no match at all, and say there wasn't any frogs in here, you wouldn't have any matches throughout the whole string. You just return an empty string. So that, I feel like that makes a lot of sense to me. Can I try to code this logic out?
Yes, please. And we're getting close to time, so I suggest you pick up the pace a little bit.
Yep. Okay. Yeah, that makes a lot of sense. Okay, so let's define a function. If I can spell, let's just call it find small substring. That makes sense to me. I'll take in the sentence, which is just gonna be S, W for words for short. Okay, so what are all the things I need? I'm looking at the drawing mode. There's a lot. So I need the target frequency. It's what I named it. Target hash map. It's gonna be a hash map of all the words. Similarly, I'll need a current freq as well to track what's currently in our window. So that'll be default dict. After that, I will need the two variables, the cur and needs, to track, how many matches do I currently have? Needs matches is going to be the length of our target frequency dictionary. And then cur matches is how much we currently have that we'll compare against. Is that all that we need? No, we also need the result, which ultimately I'll have it be a tuple for now to store the left and right pointers, the indices, to get the actual substring from it. You also need the minimum length, which I have ML in the drawing, but again, that'll be like positive infinity at first. It'll be, for sure, be overwritten. And now we need our 2 pointers. So we have the left pointer to 0 and the right pointer will be in the sliding window itself. Cool. Okay, so what do we do on each iteration? So for sure, we're going to include the current word, but let's just have some syntactic sugar. Let's call it car, sure. And then with that, we're going to add that into our current frequency, whatever it may be, whether it's a match or not. I just didn't include it in the drawing. That's okay. And then we ask, with this word, with its certain frequency, is that word in the target frequency and its value as well? Is the frequency that it currently shows up equal exactly what we need? So if there's like 5 U's and we have 5 U's, that's amazing. Then we're gonna increase our current matches to 1. And then this is where it gets, I'm gonna scroll down just a little bit. And this is where it gets a bit interesting, because if you do have, in this case, 3 of 3, well, that's fantastic, but you might need to shrink your window from the left. So if you have current matches equals the need matches. If you have an exact match, 1 for 1, well, let's get that length, which again, like I said, is the delta between these 2 pointers. If it's less than the minimum length, well, that's fantastic. Let's update that minimum length like so to the delta between the 2 pointers, and then update the result as well of these 2 indices of where you currently are. So left and right. So now the logic to actually shrink our window from the left. So let's write some more syntactic sugar. Sentences at the left index will be the left car, because why not? The first thing we'll do is exclude it from our map that kind of tracks everything that we currently have. So our map at the left car, let's minus it by 1. And then here, what's super interesting is if you decrease that frequency and it dips below the number that you need in the target hash map, then, you no longer have a match. So only then are you going to decrease current matches. So basically, to repeat that, if left car is in target frequency and the current frequency of that word is less than, and it dips below target frequency of, again, left car, then only then are you going to do cur matches minus 1. Great. Because you might exclude a word that wasn't required in the first place, and that's okay. You go on in this while loop on line 30. But either way, you're going to add from the left to exclude that word. So after that's all said and done, after the whole while loop, what you can do is, well, you have the shortest substring, right? So, but I remember in the case where if you couldn't find anything in the first place, so in which case result would be empty, an empty tuple, then you just return an empty string. Let's scroll. No, I'm not. But otherwise, you have the answer. You have the left and right pointers. So in which case you're going to return that. But to make it a bit easier myself, I'm just going to deconstruct. Let's call it start and end for result. And then I'm going to join them. I remember it's space delimited because that's how the answer should be formatted, from the start to the end, which is exclusive. So we need the +1. And that would actually be the answer. That looks right to me. Should I do an extra verification check?
No, I understand what you're doing. Can you verify the time and space complexity?
Yes. So the time complexity would be, it'd be S plus W, where S is sentences and W is the words parameter, because I think we're having to iterate over both those parameters. So first to create the hash amount for words, and then S for the actual string. The space complexity would be S in the worst case if the answer was the entire string that you'd need to take a substring of. But it would be big O W if in sentences every word was unique and you had to store all of it in your dictionary. So I guess it's more depends on the input, but yeah, I think that'd be it.
Okay, for this next problem, I'll also paste it. Okay. You've been tasked to help a small village. Find the best place to install a new well. You're given a 2D grid where cells are empty, a house, or a tree. People can walk up, down, left, and right, but they cannot walk through trees or houses. Place the well that minimizes the total sum of distance from all the houses. You can see an example.
I recognize this problem. It's obviously LeetCode 317. Yes, but it's phrased differently. I've been silent too long. I should start talking. All right, yeah, I have a few questions up front. Can we be given an empty grid?
No.
Okay, and is it possible to reach all the houses from the well?
Not necessarily.
Oh, interesting. Okay. Are we guaranteed at least one house?
Yes.
Okay, cool. And what are the dimensions of the grid?
Pretty large.
Okay, sounds good. Okay, so let me real quick in drawing mode, I had scrolled down, but let me redraw this real quick. So it seems like you have T for tree, empty space, tree, and then H for house. Okay, cool. So it looks like the output is 3. So why is that? Okay, so yeah, so I see. So if you place a well right here, then the answer is 3, right? Because if you put a well here, then to this house, it take 1 step. Great. You can go top right, bottom left. But to the other house, it takes 1, 2. So overall, 1 plus 2, that'd be 3. That's the answer, because that's the shortest I see, because that's the minimized total sum distance from all the houses. So inversely, if I put it like somewhere like here, it would take 5, right? 1, 2 to this house, 1, 3, 4, 5. Yeah, so that's shorter. That's not what you want. Okay, gotcha. That makes sense. So off the top of my head, because we want the shortest distance, I mean, we can just use, that's terrible, BFS, right? But concretely, we loop over every single cell. So that'd be a nested for loop. And if it's an empty space, then you can run the BFS function in that to ask like, hey, if I put a well right here, what's the total distance to all the houses? So for example, in the first iteration, if you put one here, and I don't think I'll actually mutate this matrix, but it would be to house 1, it'd be a distance of 1. And then to house 2, it'd be a distance of 4. 1, 2, 3, 4. Add them together, that'd be 5. So I feel like I can track that in a variable, just that number, but I do recall a constraint where you might not be able to reach a house. So it might be disconnected. You might have like 2 trees here, in which case this house is not very reachable at all. So if that's the case, we definitely want to disqualify the placement of this well in this iteration as a consideration. So we have to store not just one, the distance, but also the number of houses that the well can reach. So just thinking of another data structure, I could spin up another, a matrix. Oh God. That would be the same dimension. So 3 by 3, that looks terrible. And in each one, I can keep track of the two things. The first number could be the total distance from the well to the house, to all houses. And then the second number could be the number of houses reachable. So it'd be 0 to 0 initialized for pretty much everywhere, So on that note, I do have a question. So is the number of houses fewer, like they tend to be fewer than the number of empty spaces, like it is here in this example?
Yeah, this is a small village, so there aren't many houses. There's just a lot more empty space.
Got it. Okay, so that changes the requirements a little bit. So I'm going to take the opposite approach. So I'd prefer not to run BFS on every single white space. In this case, concretely, it'd be 5. But I'd rather run it on just the houses because there are fewer of those. I'd rather do that because although that overall time complexity seems like it would remain the same, I think this would technically still be faster and therefore more efficient. Because I just need to run BFS 2 times, not the 5 times. There aren't as many houses. Okay, so on that note, I think I need to for sure know the number of houses as well that there are in this grid for me to even know, like, hey, can this well, if it's right here, reach all the houses? In this case, it can't because it can only reach 1 of the 2. So, okay, so I'm going to go through a little dry run. So if I go through this grid as a nested for loop, obviously the first BFS at dispatch would be from this house on row 0, column 1. Using BFS, the first 2 empty spaces I'd queue up would be the ones right next to it, the ones to its left, and the one down below. What I can do is overwrite, where those coordinates are in our external data structure. 2 things: the distance that it took from the house oppositely to reach that well, and then the number of houses that well can reach. So obviously for both the rightmost numbers and number of houses, they can both reach 1 house now. The distance would be 1, right? Because it's 1 and then 1. From there on out, we have these 2 queued up in our queue because as per BFS, I'm familiar, you use a queue. You'd queue up this space, but I guess you'd queue up this space twice. So that's kind of an issue. Okay, how about this? So like I said before, everything is 0 initialized, right? When everything starts out, no empty spaces have reached any houses, so it's 0. The first time you run a BFS, for example, you know that it will be 0 initialized. If you ever look at a space and you say, from here to here, you say, hey, I've reached 0 houses. Okay, I can visit it. And when you visit it, like we saw in the first iteration, you update it to the number of houses that it can reach as well as the distance. Here, it'd be 2. It'd be 1, 2. So you keep track of the distance in their queue as well. But the second time, when the top left coordinate was queued, you look down. Well, do you consider it? This time you don't, because you pass in the number of houses. You say, well, I've already visited this house. We went from 0 to 1. I'm not going to visit that house again. So that's how we know. And when you dispatch the second BFS, you only visit houses that have one house visited. Then you increment it to 2, and you wouldn't visit again if it's 2. So I think that's a good way of not requeuing visited cells. So finishing this, you would not queue this up a second time, but you have these 2. So for this cell right here, obviously it'll be from 0 to 1 house reachable now, which is this one. And then you increment, the total distance it takes to get there from this house, which is true, 1, 2. And then lastly, with these 2 cells queued, you'd queue up this one just 1 time. And you modify it to be 1 and then distance of 3, because it'd be 1, 2, 3 as the shortest path. Okay, cool. So you're done with that BFS. You return to your nested loop where you then have a tree. You don't dispatch a BFS. It's only on houses, not this entire row or here all the way until you get to the very last house, the last BFS. So the same thing will kind of happen, but I almost forgot. When you're done with the BFS, I'm going to increment the number of houses to 1 because we found a house, and to know not to revisit any houses for the second and possibly subsequent houses, which there are none here. So for this house, obviously the first cell in queue would be the one to its left. Well, you've reached 1 house. This is the second house you're gonna reach, so that's great. You're gonna queue that, increment this to 2, add 1 to 2 to get 3, because it took 1 to get here. That if you place a well here, it takes 1, 2, 3, a distance of 3, which is accurate. After that, you queue these 2 cells, in which case you're going to increment both to 2 and then add 2 to their distance. So 1 plus 2 is 3, 3 plus 2 is 5, because right here it'd be 1, 2, 3, 4, 5. Okay, cool, that works. After that, you queue this one, which you're going to increment to 2, add 3 to here to get 5, and then in this queue you're going to queue up the very last one, in which case, hey, it's a 1, so you increment that, and then the distance you add 4 to get 5. And to make sure I got that right, 1, 2, 3, 4, 5. Cool. Okay, so at least with that, we have all the info we need in this external data structure. I guess it cannot be, oh yeah, you gotta increment houses as well, because there's a total of 2 houses. I guess we can't help but have another nested for loop right after. Doesn't change the time complexity, I don't think, to check every single cell in our matrix to say, oh, it's asked 2 things. 1, have we reached the total number of houses? And if it's 2, in this case, then we have. Also, if so, is the distance the shortest it is? So 5 would be the shortest first, so you keep track of 5. But once you get to 3, you say, well, 3 is the shortest one, so the distance of 3 would be answer. And ultimately, there are 2 3s, but we just care about the number. So we'd return 3, and that'd be the result. So I like that, although I do recall another edge case where essentially with our input, it can be a disconnected graph, in which case certain houses can be, blocked off by trees. So in that case, we just return -1, and that just happens when the number of houses from every single empty space is not the number of houses there are in the grid. So I'll factor that in the second nested for loop. So I like that a lot. Can I code this up?
Sure.
Okay, cool. So let's get started. I'm scroll down. I don't know, let's just have a class because I feel like we're going to have multiple functions, so best to organize it. Maybe call it well placement, sure. To have one function called place, which will take in just the grid, which is the 2D matrix. The first thing I'll need is definitely my matrix, my external data structure, in which case, like I said, I'm going to initialize everything to 0, 0 for the 2 fields, the total number of distance, and the actual house. And this is for every single, every single cell. So that's the matrix. What else do I need? I need the total number of houses, which starts at 0. We're guaranteed at least one house, so it works out. Then I'm going to start the nested for loop, sure, with I and j of where we currently are over our grid, and j for the column. Fantastic. And for each one, we'll inspect and say, well, where I'm at right now, is this a house? Because I only run BFS if we're on a house, because it's technically more efficient. If so, I'll call my helper function, which I will soon write. So let's call it BFS for short. I need to pass in where we currently are, where I'm going to seed my queue. So I and j, sure, as a list. But we need a bunch of other stuff. We need the grid, we need the matrix, and we need the houses for the visited functionality. And I can't forget, but after the BFS, you're going to increment the number of houses there are, because you're going to keep track of it for later on, to figure out from this, well, can I reach all the houses? Is it even valid to consider? I'm going to place it to do, because I'll get back to it, but let's implement the BFS, where, again, we'll need, sure, it's called the source, that will seed our queue, grid, matrix, houses. It's all the same parameters. So first, let's get our queue, which is going to actually be a deck. I'm going to seed that with, so two things, the source of where we are as state, but also the distance as well, which starts off at 0. So according to BFS, I'm going to keep going in this algorithm so long as there are still cells in the queue. And for each one, I'm going to pop the very left because I want FIFO, and then get from that, extract from that the current of where we currently are, the I and j list, as well as the distance, dis for short. So after that, I want to go over and loop over 4 directions, right? Because in the description, I see it says people can walk up, those 4 directions. So I'll deconstruct both coordinates, dr and dc, for the row and column, respectively, in a bunch of directions, specifically 4 of them. And the order doesn't matter, but first let's do the top, which is -1, 0. Then go to the right. Then you go down. Then you go to the left. I believe that covers all ground. So for each of these directions, I want to get the new direction that I'm going to be at, which is going to be our current, which is the I and j, 0 with 1 being the x, the I in this case, plus the direction offset, and similarly the column with the column offset. So with this, I'm going to scroll down just a little bit. Cool. With this new row and column, there are, and I didn't go over all of them, but there are a bunch of edge cases where, if you're out of bounds in any way, for example, if your I, your x is ever, in the negative, or it's not, it stretches beyond the last row, then that's a problem. You're literally out of bounds. You should just not queue up the neighboring node. So similarly, we can do a similar thing for j, right? So length of the grid, sure, like so. If it's out of bounds, if it's, in this case, if it's in bounds, then you can queue it up. If not, you're not going to do whatever's in this if statement. So after that, it's also 2 more things. It's the visited matrix. So is the number of houses in that neighbor what we expect it to be? So matrix at I and j, you can access it now because we're not out of bounds. It's the second element technically. You only do if it's equal to the number of houses that you expect, because you're about to visit it. So if that's the case, but you have one more, which is that neighbor an empty cell? Because if it's tree, you can't go through trees. That's quite obvious. If that is an empty space, and to clarify, just to make sure I'm not insane, every cell that's empty is a white space, right?
Correct.
Okay, cool. Okay, just making sure. So if all those things ring true, then we can do a bunch of stuff. We can queue it up, obviously, but you need to, modify the matrix at that neighbor of the 2 things we need to keep track of. So first, the distance, which is the distance plus 1 because you made like another step. But also, you need the number of houses that it's now has visited, from that well of where it'd be. Houses plus 1, great. And lastly, I'm going to append, the state of the queue, which again is ij, the new coordinates of where we are, as well as the distance, again, plus 1, because you made a step. I believe that would be the BFS. I can double check that. But back up to when we run BFS and we have our 2D matrix already. Let's loop over the matrix again, but this time we need a result, which keeps track of the minimum total distance. It'll start off like in the previous problem, positive infinity. It will definitely be overwritten. And then have the nested for loop, which I'm going to do something absolutely terrible and copy and paste to save some time. So with this nested for loop, you only will consider a space if that well can be reached by all houses, because that's the requirement. So where you currently are of the second element, the number of houses, if it equals the total number of houses, which on line 65, or line 60 rather, that's the number of houses that we'd have, then you take the minimum between, the result shortest distance right now and, the actual distance that we also stored in the matrix is the 0th index element, and then you update that as appropriate. So after that's said and done, you have one last thing to do. Since you have the answer, you're going to turn the result, but only if it's not, and I have to rewrite this, only if it's not positive infinity, because that means you actually found a well that could reach everywhere. Otherwise, like I said, you return -1, because every well couldn't reach a house, or at least one house. So I like that. I believe that all works. That's right. And the time complexity would be, if we're given this n by m board, it'd be n squared times m squared because of the nested logic. The space complexity would be n times m, just because of the external matrix that we're, having to spin up. So, yep, looking over my code. Yeah, I think that's good.
Is there anything else you want to check?
Is there anything else? Probably, now that you say that. Yeah, I kind of did a dry run. Let me just double check everything, like in our BFS. Obviously, you make a new queue, you seed it, you keep going as long as there are elements. You go through each 4 directions for the new one. And then you go through your gauntlet of if statements that you only go to the neighboring cell if it's inbounds. If you can visit it, and if it's an empty space. I see. Okay. No, I see it. So I was checking the matrix, if there was an empty space or not, but I need to check in the grid because that's where the houses, trees, and the empty space would be. So I'm gonna double check everything else too, just to make sure I mutate the matrix of those two things as appropriate, and then queue it up. That makes sense. Going through the main logic, I spin up the external matrix, number of houses, simple loop to go over the entire grid and running BFS on only the houses, and then getting the results. Yeah, okay.
Looks good. Thank you for that. You did very well. Not many candidates can complete both problems. So, did you have any questions for me?
Yes, I do. Would you pass? I mean, did I? I have no idea. And if you learned something today, please make sure you like, comment, and subscribe. Thanks.